All right, this is a big section. Buffers. Buffers are big time stuff. They protect us from the nasties that get into us, whether we drink it, eat it, or whatever. And it protects us from the chemicals that are in the mixture that we consume that do not belong in our bodies. Particularly those of severe pH levels, like high levels of basicity and high levels of acidity. A mixture of both acid and base, weak acid and weak base, is what makes a buffer. It has to be weak. Strong acid, strong base, and their conjugates do not create buffers. They just are separated. But these compounds stay together. What I mean by stay together is that the acid doesn't break down by maybe 2-3%. The base doesn't break down by maybe 2-3%. The remaining 97-98% then is allowed to attack a severe acid or severe base that we have encountered internally. So, in order to figure out how this works, we have to use something called HendersonHasselbach equation. Now, the way that we know that we have buffers in our system working for us is when we consume something like, say, a can of Coke or a bottle of Mountain Dew or whatever it is your soft drink of preference happen to be. The pH of most of those soft drinks is in the neighborhood of 1 to 2. That is very, very, very acidic. And if your stomach did not have a buffer system, you would basically destroy the lining of your stomach. But because of the buffer within the mucous membrane that lines your stomach, your esophagus, your mouth, you're able to, it is instantly neutralized by one part of the two parts of the buffer. And the base part of the buffer will neutralize the acid part of the attack, and vice versa. So, let's take a look to see how this is done. First of all, we're going to take a look at a generic weak acid, which we'll call HA. And this breaks down a little bit in water, hence the aqueous, and the conjugate base is A negative, because this has an extra proton than this, otherwise it's the same thing. That's a conjugate acid-base pair, and they are weak. We are saying that these are indeed weak acid-base pairs. Now, that means that we can write a Ka expression for this, and that would be what this is here. Ka equals H positive times A negative over HA. And then what we're trying to do is find the pH of a buffer solution with this equation. So I'm going to remove everything except the H positive on the right-hand side and multiply by the reciprocal of A negative over HA to both sides. And I get H positive equals Ka times the concentration of HA over the concentration of A negative. Now the next thing I'm going to do, since I want pH, I need the negative log of H. So if I take the negative log of the left side, I have to take the negative log of the right side. And now, you have to remember what logarithms mean are exponents of 10. Log, there's no 10 there, but it's an implied 10. This is log base 10, means exponent base 10. So we're dealing with log or exponential mathematics here. So follow along on me when I talk about logs here. So the negative log of H positive by definition is pH. Now, when you multiply, when you have like bases that are multiplying, they're exponents that are being multiplied, you are actually adding the exponents. Like 10 to the second times 10 to the third is 10 to the fifth, because 2 plus 3 is 5. Log is exponent. Logarithm is another word for exponent. It's the same thing. And the base, like I said, is 10. So that means these two are being multiplied, so we're adding their exponents. So the negative exponent of Ka is being added to the negative exponent of the fraction HA over A negative. I mean, you were taught that in algebra. You may not understand what log means, but if you use the word exponent in your head, you might be able to follow along where all this stuff is coming from. Now, again, negative log is a mathematical process that is described by the letter lowercase p. So if I have negative log of Ka, I can also call that pKa. Just keep in mind that means negative log of Ka. Now that leaves this over here. Now, the deal with HendersonHasselbach, these German scientists, is they wanted everything to be positive because people make stupid mistakes with negative values. And so what they did was, they didn't want a subtraction here, they wanted an addition. So they took this fraction and flipped it. And you can do that when you take it to the -1 power. Okay? So that becomes negative log of the fraction a negative over ha to the -1 power. Well, when you take an exponent of an exponent, you multiply the exponents. So negative log times -1 is positive log. And this gives us a negative over ha, where a is a weak acid, and a negative is a weak base, and ha is a weak acid. So we use the words base and acid, or you use a negative and ha to remember the formula. This is called the Henderson-Hasselbach equation. Okay, that's described in the script. Henderson-Hasselbach is a big deal. And it's because of Henderson-Hasselbach that we don't have to deal with common I, which is why we really like this. Okay? So, let's take a look at the odd number problems based upon your assignment that you have coming up for this. We have a buffer that is made with 45 milliliters of 0.15 molar NaF and 35 milliliters of 0.10 molar HF. Now, HF is a weak acid, and NaF, when it breaks down in water, is Na positive plus F negative. That is the conjugate base. So that's what we're using in our buffer. Okay, and we know it's going to be 0.15 molar because it breaks down evenly these. We don't care about the sodium, but we do know that this is going to be 0.15 molar. The problem is, when you have solutions of a weak base and a weak acid, they are diluting each other. They are making themselves less concentrated. So we got to figure out the concentrations of these things after they dilute each other. So we're going to take this 45 milliliters right here and change that to liters. Multiply that 1 liter over 1,000 milliliters. And we get 0.045 liters of F negative. And we're going to multiply that by the concentration, which is 0.15 moles per liter. Now the reason why we're doing this is because we have to figure out the concentration after the total volume of the two solutions are added together. So we have to know how many moles we have of this. So we cancel those out, and we multiply 0.15 times 0.045, and we get 6.75 times 10 to the negative third moles of F negative. Now we're going to do the same thing right here with the conjugate acid. We have 0.035 liters of, not F negative, I'm sorry, it's HF. Okay, and we multiply that by 0.10 moles per liter. Liters cancel out, and that gives us 3.5 times 10 to the negative third moles of HF. Okay, now, since I'm looking for concentration, I have to divide these by the total volume. Well, the total volume is the sum of these two together, which is 0.08 liters. So I'm going to divide 0.08 liters here and divide by 0.08 liters here. So dust off my calculator. All right, so it takes 6.75 times 10 to the -3rd divided by 0.08, and I get 0.0844 moles per liter. Of F negative. And here, 3.5 times 10 to the -3 moles divided by 0.08 liters. And I did something wrong here. Don't ever use two division signs, they absolutely hate it. And you get 0.0438 moles per liter. Okay? And that's of HF. Now we're ready to plug that into HendersonHasselbach, remembering that the Ka is 6.8 times 10 to the -4. So, pH equals negative log of 6.8 times 10 to the -4 plus the log of the concentration of the base. And the base here is 0.0844 moles per liter divided by the concentration of the acid, which is 0.0438 moles per liter. And so we go ahead and plug that in, negative log 6.8 E -4. And make sure you close the parentheses on that, plus 0.0844 divided by 0.0438. And you get 5.09 for our pH. Okay? So if a substance were to attack us that was acidic, the NAF is going to react with it. If we have a basic solution attacking this buffer, then the HF is going to attack it.